So back in the day, somebody introduced you to the idea of BFDMAS in order to work out the order in which you should execute operations. BFDMAS was, of course, brackets, exponents, division slash multiplication, and then addition slash subtraction. Well, that's fine, but now that we're getting into more complicated functions, where exactly did square root fall into that acronym? Or ln, or e to the x, or sine and cosine. Those things didn't feature in BFDMAS because BFDMAS was intended for teaching algebra skills in grades 7, 8, and 9. And now that we're beyond that, we need sort of a new set of words in order to describe the pieces of functions that we need to work on. So in this particular example I have up there, there are 3 pieces to this. The first one, and the most important one, is the function itself. So in this case, the function that we're dealing with is the radical operator, so a square root. The next most important piece that's in there is this thing, and this part, everything that is inside of the function, is called the function's argument. And so that's 2x minus 3. And all the stuff that's on the outside is sort of the least important thing to the function. That's this and this here. These are external modifiers. So we have a multiplication by -5. And we have add 7. Okay, good. So what these pieces do is the function is really what determines the input-output. It decides what numbers can go in. Certain functions only accept certain numbers. For example, you cannot square root a negative number. So this function has decided that there's a certain flavor of numbers that it will accept, and then there's a certain flavor of numbers that it will output for you. So that's why this is the most important thing. It determines the shape of the function. It determines what numbers get spat out. The argument is the next most important thing because it's going to determine what numbers get fed into this thing. And I already pointed out that radicals can't accept negatives. So the argument there, that 2x minus 3, that's what determines if a number inside of here is negative. So this is why it's second most important, that the inputs are determined by this structure. Once you've determined the value of the argument and shoved into the function and gotten your answer, whether you multiply it or add something to it doesn't really matter anymore because the function has already done its job, and we're just tweaking the output. So these things get done last. So what we're going to do then is we're going to reframe BFDMAS in terms of these 3 bits. So the first thing you need to do whenever you're trying to reduce an expression, number 1, is you evaluate the argument. Okay, so you figure out what number is going to go into the function. Number 2, you execute the function. So if it's a square root, you square root it. If it's a ln, you push the ln button. If it's e to the x, you do e to the whatever and get your answer. Number 3, after you've decided what number's going in, you've executed the function, you modify appropriately. So you apply external modifiers. So that's your new BFDMAS. Evaluate the argument first, then execute the function, and then apply the external modifiers. And you must do those things in that order. So I'm going to take this function that we have here, and I'm going to actually evaluate it. So given f, I'm going to try and evaluate f at 11. Okay, so I'm going to put that number in there, replace all the x's with 11s. Okay, so my new order of operations here says that, oh, let's get this crap out of the way. Perfect. It says I'm supposed to evaluate the argument first. Well, that's this chunk here. So, the BFDMAS stuff still applies, or we haven't thrown it completely out the window. We've just enhanced it a little. So I should be doing the subtraction first. 11 minus 3 is 8. And then 8 minus 2, or 8 times 2 is 16. So if I evaluate that argument, I end up with 16 inside my function. So once, well, check. I have evaluated the argument on this particular expression. Next thing I'm supposed to do is execute the function. So I have this 16 sitting inside of a square root. So I'm going to square root 16. The square root of 16 is 4. Okay, check. I've executed the function. Now that the function's been executed, I can apply those external modifiers. So negative 5 times 4 would be negative 20. And negative 20 plus 7 would be negative 13. Therefore, the function at 11 is negative 13. So if you went all the way out to an x value of 11 on a sketch of this function, the y value would be at negative 13. So this one looks a little different, just because of the notation. It's got a 5 sitting over top of something, which looks like a fraction, but this maybe will cause you less stress. There were never such things as fractions. There were only rational expressions. So I'm going to rewrite this so that it looks like all the rest of the functions we've had. We pull that 5 out in front. And then I'm going to use negative exponent notation to pull this thing out of a fraction. So it doesn't look like a fraction at all. It would be h of x equals 5, 2 times x minus 7 to the negative 1 plus 3. And if I do that and use better penmanship, there we go. I've taken this thing that looked like a fraction and I've written it as something with an argument, a function to apply, and 2 external modifiers. So when you see expressions like this, if the fraction causes you heartburn, you may want to choose negative exponent notation in order to make it look like all the rest of the functions. So now that I've done that, I'm going to show you how to evaluate one of these. So h, let's do this at h at 9. So in goes the 9. So step 1, evaluate the argument. I have to find all the stuff that's in there. That's this chunk of things. And I have to get that done. So 9 minus 7 is 2, and 2 times 2 is 4. So my function here would be 5 times 4 to the exponent negative 1 plus 3. All right, now, next step, once that's done, is to evaluate or execute the function. So 4 to the negative 1, you could type that directly into your calculator and it will give you 0.25. So that's an option. Or you could write that as 1 over 4. That's an option as well. I'm going to use the fraction option because ultimately we should be moving towards fractions. So h9 is, that would be 5/4. So the function has been executed. Actually, let me slow down. I skipped a step there. That would be 5 times 1/4. Now the function has been executed. If I apply this external modifier, 5 times 1/4 is 5/4. And 5/4 plus 3, I will need a common denominator. So 5/4 plus 3, there's 4 quarters in each, and there's 3 of them. That means a total of 12, which gives me 17 quarters. And 17 quarters is 4.25. So if you use the -1 button on there and rendered this as 0.25, 0.25 times 5 gives you 1.25, and 1.25 plus 3 gives you 4.25. It's the same answer. I would prefer the fraction, and if you are pursuing a career in engineering or physics or mathematics or finance or anything like that where it's number heavy, you need to prepare yourself for that, because fractions are the expectation, because they're superior in their answers. There's no rounding, there's no errors. That's the best way to write your number. If you'd like, if you're not confident in your fraction skills yet, do it both ways. Do it as a fraction, do it as a decimal, and then make sure that they match at the end. So the practice problems have a whole mix of things from the different functions. They have sines and cosines, they have parabolas, they have cubics, they have rationals, radicals, exponentials, and logarithms, which are the 7 base functions that we're going to work with. But all 7 of those functions follow the same 3 sets of rules. You must evaluate the argument first, and then you must execute the function, and then, only then, do you apply the external modifiers. We have an exponential here, and we need to solve it, or evaluate it rather, when x is 18. So this function isn't any different than any of the other ones. You have an x sitting here, and you've been instructed what number to put in for the x, so that's what I'm going to have to do first, put this in there. So m at 18 will be 3 multiplied by 2 to the exponent 1/5 of 18 minus 3, minus 6. So this line is just that line with the x replaced with an 18. So we have to go through order of operations. This is the function, right, the exponential. So the argument of that exponential is all this junk up here. So if I look at it, I'm going to have to take the 18, subtract 3 first. So 18 subtract 3 is 15. I'm going to write all this nonsense down again. Uh, 18 minus 3 is 15. And I'm trying to be very careful to keep this stuff up in superscripts and these 3 numbers on the base level. So next thing, I have to finish the argument here. 1/5 of 15 is 3. So 1/5 of 15 is 3. Again, trying to be careful to keep the exponent as a superscript and everything else on the base floor. So I've simplified the argument now, so I just need to actually execute the function. 2 cubed, that means 2 times 2 times 2, which gives you 8. So m at 18 is 3 times 8 minus 6. And I can finish by applying those external modifiers. 3 times 8 is 24, and 24 minus 6 will be 18. Now that's just a happy coincidence that this number and this number ended up the same. It can happen. It didn't happen for any particular reason, just the numbers I chose. So we have another exponential here. This one, instead of being base 2 exponential, this one is base 3. But the process is exactly the same. I have a spot for an x, and I know what number I need to put there, so I just need to do it. So my function p, evaluated at 9, is going to be all this stuff with that 9 filled in for x right there. So like all functions, I have to deal with the argument first, right? The stuff that the function is actually going to work on. So looking in there, I'm going to need to do 9 minus 5, which is 4. And to finish her off there, I need to take half of 4. Half of 4 is 2. And now that the argument has been simplified down to a single number, I just have to execute the function. So 3 squared is 9. And 4 times 9 is, come on brain, 36. And 36 minus 10 is 26. So the value of this function, p, when x is 9, is 26. So yet another exponential function. This time we've got the base 10. And maybe you're catching on here. I can put any number here. It doesn't matter. I'm going to use 2 and 3 and 10 a lot. 2 and 3 just because they're easier to work with. They don't blow up quite so big. And 10 because your calculator actually has a button, the log button, that will let you solve these things when we get to the next section. So that said, even though this one, it's a fraction and it's got a negative in it, we're not going to panic because it is exactly the same process as everything else we've done. You've got an x there, you've got a number, in it goes, work it out. So I need to find the value of q when x is negative 7. So I leave the 5, I leave the 10, I leave all this stuff, except the x gets replaced with negative 7. All right, it's even got a negative number in there, so spicy. But you can do these. Negative 7 plus 6 or plus 1 is going to be negative 6. I'm going to fill that in. Negative 7 plus 1 is negative 6. All right, and if you think about your integers from grade 9, negative times a negative gives you a positive answer, and 1/3 of 6 is 2. So this mess here is going to be positive 2. Now, if that caused you a little bit of panic, there are a few ways you can look at that. This thing, that's not really a fraction. There have never really been fractions ever. It's just a division that hasn't been done yet. So if you take that and you sort of flip it around, that thing is the same as taking negative 6 and dividing it by negative 3. So if you've been struggling with how to manage fractions for the last few years, just keep that in mind, that fractions were always a lie. You can just do division because that's really all they ever were. What are we doing? Exponentials. So I've got a 10 squared here, that's 100. And 5 100s is 500. Looks like 560, doesn't it? There we go. And 500 minus 21 will be 479. So the value of this function, q, when x is negative 7, is 479. Okay, so we've got the logarithm function involved here. So this will be a new one. I don't think you've ever seen this before. And we're not going to dwell too much on what a log means or what to do with it, because that will come up a little bit later in this course, and it will come up again if you take the grade 12 advanced functions class. But for now, we're just going to treat it like a button on your calculator. We're going to work through just to show you that this new function, even though you've never seen it before, behaves exactly the same as everything else we've been working on. So I see an x, I see a number. What are we going to do with it? We're going to put her in there, just like we always have. So a evaluated at 15 is 6 times the logarithm of 2 times 15 minus 3 plus 5. So this is a new function, so you maybe haven't seen the argument laid out quite like that. That's this piece. Right? That's what the log is going to be working on. So we need to simplify that first. 15 minus 3, that's 12. All right, and we have to work on this part here. 2 times 12, that's 24. All right, now this thing, I can't do this one in my head because this one doesn't come out cleanly. So I'm going to have to get a calculator, and I'm going to have to type in log 24. But that's not too hard because everyone has a calculator nearby at all times. So if I plug my machine here, which I've left somewhere else, not on me at all times, but near me at all times. Log of 24 comes out as 1.38 and a whole bunch of other decimals, but we're just going to keep 3 for now. 380 ... And that's it. That was the only thing that was new because it was a logarithm. I had to use my calculator and find the button on it that said log. So if you have a calculator and you can zoom in on her, there she is, the log button, L-O-G. Then you can do this. So I have to take this horrible number and multiply it by 6, which, since I already have the calculator out, let's let my brain cool down a little bit, 8.281 ... That's only accurate to 3 decimal places, so we're just going to put that in there to remind ourselves of that. And we have to add 5 to it, which gives us 13.281-ish. All right, so it didn't matter that it was a new function that you'd never seen before. When you're presented with something like this and you're handed an x value, you just take that number, pop her in, work it out. Always evaluating the argument first, then executing the function, and then applying any external modifiers. So just like exponentials, logarithms come in many flavors. The last one was a base 10. This one is a base 2. You can see it's base 2 because it's got a little 2 down there. Even though I've changed the base though, same idea still applies. I have an x, I have a function, in it goes. So b evaluated at 11 will be 7 log base 2 is 4, 11 minus 3 plus 2. So I've got my argument here. I have to get that worked out before I can apply the function. So I'm going to need to do 11 minus 3, which is 8. And 4 times 8 is 32. And here you need a little magic, or a better calculator than what most calculators have. You generally don't find a log base 2 button or a generic log, right? Log y of x. You might have something like this on your phone. I know that the phone calculators have started to have them, and I have started to see standard calculators show up with this button on it. At this point, we're going to have to stop here unless you know the value of log base 2 of 32. Now, like I said earlier when we were talking about the other logarithms, this function is talked about a lot in the grade 12 course. So for now, if you're trying to evaluate it, you can just get to here and you can just stop. So why would I make you do this if we can't actually answer it? Well, the point of putting the logarithm in there isn't for you to actually understand how logs work yet. It's for you to see that it doesn't matter what function is up there. If you've got a number, you put it in where the x is, and off you go. Just because my obsessive compulsive disorder won't allow me to actually stop here, I'm going to tell you that the value of this is 5. Now, if you have some number sense and you're pretty good with exponents, you might know that the number 2, if you raise it to the power 5, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the power 5 is 32. So because 2 to the 5 is 32, log 2 of 32 is 5. These things are related. Let's just stew on that for, let's say 12 months, and we'll reconvene in advanced functions to go over that a little further. But for now, 7 times 5, that's 35. And 35 plus 2 is 37. So the value of this function b when x is 11 is 37. All right, so just for completion, we'll do one more logarithm. This one is no longer base 10 or base 2, it's base 3. And you can tell by the little 3 wiggling down here. So I've got a value for x, in it goes. I'm sure you're tired of hearing me say that, but I'm going to say it one more time. Here's my c, put in the -2. -2 goes in there. We have to work out the argument before we can apply the function. So 5 and -2 gives you +3. And 3 times 9 is 27. And we're stuck at another spot here where unless you have a calculator that can evaluate log base 3, we're going to have to stop. So you can put a little star there and say, I don't know, my machine doesn't work. If you thought about the last example, when I had a 32 here and a 2, the answer was 5 because 2 to the power 5 was 32. Here I'm asking 3 to what power gives me 27? So again, you don't have to know this yet. I'm just throwing it out there because I can't leave it unevaluated. 3 to the power 1 is 3. 3 squared is 9, and 9 times 3 is 27. So because 3 cubed is 27, then the log base 3 of 27 is 3. So again, stew on that, and we'll circle back to it in advanced functions. Just in the spirit of finishing, 4 times 3 is 12, and 12 minus 7 is